Hey everyone, I'm Daniel Gotz and I'll be taking over Paul's Patreon for August tutorial. Today, we'll be learning how to create an animation like this. We'll start off by prepping our perfume bottle and quickly setting up a flip sim and colliders. Next, we'll create a simple infection solver to spread an attribute from our fluid to our bottle. I'll show you how to use VDB operations to create the illusion of a flip fluid forming the bottle, as well as grabbing UVs from our original bottle and creating velocities on our leading edge. I'll be releasing part 2 of the tutorial on my YouTube channel, where we'll talk all about lighting and rendering. It's Houdini time! Or as I would say, let's set this thing in motion. Let's get started with the geometry prep. So to kick things off, we're just going to put down our trusty setup geometry container. Import a bottle, that's the old bottle here. You can also use the one that you made in Paul's tutorial. You should still be able to easily follow this tutorial along. Then we will want to use a match size to center it. And I like to work in the scale between like +5 and -5 in the Z and X direction. So I'll simply transform this bottle up by a factor of around 2. Cool. So this is our bottle. It's nicely scaled now. Let's put down a null. Imported bottle. And let's prepare this for the collider now. In order to do that, we're going to want to blast each piece first. So we want only the bottle. And we want only the lid or the cap. So the bottle. Oh, sorry. No, we only want the outside of the bottle. I have a group already made for that. So this bottle here has an open hole. We're going to want to fill that with a polycap. The cap itself does not have a hole, so we don't need to put a polycap or polyfill there. Let's merge these together. Press Shift S for the nice curvy lines. Put down another null. Call this here bottle prepped. And let's drop down a collision source. Put one null out of the left stream, call this here call geo. And one null out of the right stream, call this here call vol. If you look now, we have one geometry stream and one SDF VDB stream. We're going to be using both for our collider later on. Let's draw a nice box around this. Click it here. And just say bottle preparation. Great. Next up will be the preparation for our actual flip simulation. So let me make this here a little bit smaller. Create a box. We're going to want this box here to kind of encapsulate our perfume bottle. So we can just template, or actually no, we will highlight this, template the box. And I believe a size of 8, 15, and 8 worked out for me. Next up, we're going to want to put down a copy to points. The target points are the corners of this box here. If we preview them, oops, there they are. And we want to copy other boxes on top of here. So now we have a box on each corner. Let's increase the size of these to 2. And let's put down a scatter and use the handy dandy modulo function to scatter a single point every 12 frames. In order to do that, we will do $ff, which is the subframe, modulo 12 equals 1. So if you take a look now, on frame 1, we are scattering 1 point. On frame 13, we're scattering another point. Frame 25, another point. 36, 37 actually, another point. And so on and so forth. Let's put this here to the side and create another copy to points. Well, actually, we're still missing something. If you look at this here now, the point keeps getting scattered on the same position, which isn't what we want. We want these spheres to come in from all different sides to hit it. So let's also adjust the global seed. We're going to do $f times 10. So it's going to take the frame number, multiply it by 10, and then that's going to be the global seed. With our second copy to points, the point to copy to is going to be our scattered point, and we want to copy a sphere onto here. Let's turn the sphere here into a polygon. If we actually highlight the copy to points, we will see it. We want this up as a polygon, frequency of 12, and dial the uniform scale down to 0.75. These are just sizes and measurements that worked for me. Then we're going to want to put down a mountain, which now is called an attribute noise, on the position. Then the amplitude is right. We want to increase the element size to 2 and decrease the roughness to 0. This is just to get a little bit of a little bit of a break up in the shape of the sphere itself. Next up will be a flip source. Your flip source will most likely be different to mine. What I have done in my flip source is that I have immediately, or like by default, linked the particle separation and the voxel size. So what you almost always want to do in flip simulations is link these two parameters. So the voxel size is oftentimes the particle separation times the grid scale. And the grid scale most of the time is 2. So I just put this here to particle separation times 2. In order to do this yourself, you can just copy the parameter, paste it into the voxel size as a relative reference, click here, times 2, and you are done. If we look at this point here now, we will see, or like at these multiple points in the volume, we will see we have 482 points, 1 VDB, 1 prim, 1 vertice, and we have a position attribute and a name. If we were to just chuck this into a flip simulation now, first of all, the resolution is quite low. And secondly, we have no velocity other than gravity, which would come in the flip simulation itself. So let's deal with that. What I would like is to point the velocity of the spheres towards the origin. So this 0, 0, 0 position right here. In order to do that, we need to subtract two vectors from each other. We need to subtract the vector origin from the current position. How do we do that? We simply use a point triangle here. We need to first define our origin vector. So we can simply set this to 0, 0, 0. And then we can say that our velocity is equal to, let's normalize this, origin, which is the origin vector, minus our current position. And then what I like to do for extra control is add a channel float multiplier. Oops, forgot the X here. And if we create this channel now, or like this spare parameter, visualize the velocity by clicking on V, and increase this multiplier now, we will see that we will have velocity pointing towards the origin. I will set this multiplier to 15 because that's what worked for me. And then I'll simply put down a null here, call it flip source. And our preparation for the .NET is done. Although actually no, there's still one more thing left. Remember the collision source here? In the volume tab of it, there is a voxel size which we can link. So we'll go into our flip source, copy the parameter here, and in here we will paste the relative reference. So now these two are linked up. So let's create our .NET. Connect it here to the flip source and just call this here top flip. Highlight this and dive in. We can see it's just a whole bunch of emptiness. We're gonna need multiple different things here. Most importantly, we will need a flip object and a flip solver. Let's connect it like this. What you will probably see, which is also another thing that I have changed from default, is that you will probably have a kind of like a cube here with different blue balls. In order to get rid of that, you just need to delete everything that's in the subpath, and into the guides, you need to go into particles, and you need to turn a visualization from, I believe it's either spheres or sprites, and put that to particle. It's also going to be a lot lighter to display for you. Then the next thing we're going to want to do is we have this particle separation here, and simply go back out, copy this parameter, paste it in here, and then we need something else. We need a gravity force in order to get like our liquid to fall down. we need a volume source in order to source the liquid in. And we also need a static object, which will be our collider. Put down a merge as well. Connect this here. And let's actually go one by one and set this thing here up. So in our static object, we simply want to go in here. The subpath should be the collider geo. Copy this here, go into collisions, set this here to volume sample. The proxy volume should be call vol, which we created before. Now we can see that our collider bottle is in here. So our collision is done. Next up, we're going to want to go to our volume sourcing. Initialize this here as source lib. The input should be our first context geometry, because if you remember, we piped it into the first input. We're bringing in the surface, but we also want to bring in the velocity. So you want to add another instance. Source volume should be v, and the target field is vel for velocity. Next up, I also like to add a pop drag, put it into the particle velocity and set it to something very low like 0.025. And we're also going to want to add a pop wrangle, which we will use to initialize velocity. Type this code in here. Sorry, not velocity, viscosity. F at viscosity equals channel float viscosity. Now we can simply create this parameter here. And we set it to 25. You can experiment with these values here. It's just what worked out for me. These guys are done. This is done. The static object is done as well. That just leaves us with the flip solver. The flip solver has multiple different settings that we want to change. First of all, the substeps. I usually set my substeps to 4 and 6. However, I think in this case, we can just put them to 2 and 4. Next up will be the particle motion tab. We're going to want to add an ID attribute. It's always good to have an ID attribute in here. Receding, separation, droplets, and vorticity and rest will just leave as default. If you plan to retime the simulation, it's a good idea to turn off receding. However, we don't plan to do it, so I will just leave it on. The next thing is in the volume motions tab. We want to set this here to swirly, and we also want to change our volume limit. If we take a look at this purple box here, these are our bounds for our volume. And it's a little bit too large at the moment, so I would reduce this here to 25, 20, and 25. Next up is the viscosity. Go in here, enable the viscosity by attribute, which is what we created in here in this pop wrangle. And let's solve this with adaptivity, which will just speed things up a little bit. Next up is the surface tension tab. We want to enable it and set it to 25. Go to the solver. If you have a good GPU, you can use OpenCL. I will use it. However, if your GPU doesn't have that much VRAM, I would just let it run without OpenCL. And that is pretty much it for the flip solver. We just kind of speed ran through that. Let us now import our result. Or like set everything up for the import. So we need a DOP import field. We want to choose a preset, which is flip fluid. Then we're going to want a flip compress. Oh, sorry, no. It's called fluid compress. Turn off call bandwidth, and I want to keep all of the attributes. Then we want to grab this particle separation again, put it in here. Everything is just connected. And before we actually cache this out now, let's just let this run for a second to see if everything is working well. So it is working well. However, we have way too little particles in the simulation. So let's go into the flip source and change the particle separation to 0.025. Now let's run this again. Okay, I think this is enough to just see if it works or not. Let's set this to real time. Totally forgot. Okay, so we can see that on frame 1, we're getting this first sphere in. Then on frame 13, we get the second sphere. And on frame 25, we get the third sphere. So our scattering is working, our fluid is being sourced in, and our collision is working as well. And we're also getting some nice surface tension and some nice viscosity in there. So let's put down a file cache. Then we can simply call this here Perfume Splash Flip. and cache it out. Actually, one thing that I forgot is that we might want to change the length of our timeline. The length that I cached out is 120 frames. So you can just change it down here back to 120 frames. And I will load in the cache with a file swap because I had already cached it out previously. So I'm not gonna, cache it again. Your liquids will probably look like this, just this voxelized mess kind of. And in order to get the particles back, we want to use a particle fluid surface. Change this to particles and put the visualization to velocity. And what we can do now, we can just quickly hop out, put a camera down, go into our camera, set this to 1080 by 1080. I like to use a focal length of 135. Now we're just gonna translate it, about 40 back into the Z, and we can do a quick flip book to see how this looks. Okay, let's have a look. So we get the splashes in. Yeah, this looks pretty nice. I especially like this part where these liquids here just kind of flow down the side or like the front of the bottle. So that's cool. Let's now turn these particles into an actual mesh. You can put down a null first, just for clarity's sake. Call this flip particles. Then we can put this here into a neat box. Flip sim. Just move this over here. And now we're going to want to object merge these flip particles over here. Now we have these particles. We want to turn these into a volume. So VDB from particles, set this minimum radius to 0. Then we can decrease the voxel size to 0.025. And it's a little bit holy, which we would originally, or like ideally, we would want to fix this with just increasing the point number or like decreasing the particle separation in our flip sim. However, this is another way that you can deal with that if you have a very tight deadline. You can put down a VDB reshape SDF, dilate it, and put down a VDB smooth SDF. Put this operation to mean curvature floor. And then we put down a convert VDB to turn this volume back into polygons. Nice. So yeah, as we can see, like it's not the highest resolution, but it will do for the purpose of the tutorial. One thing that we noticed though is that there are no attributes on here. So we need a velocity attribute in order to get motion blur. So let's create an attribute transfer. This is the attribute, the geometry we want to transfer to, and this is where we want it from. We do not want the color, we only want the velocity. If we double check now, yes, we have velocity on this mesh now. Let's put down a normal sub, and we can cache it out. Let's call this Perfume Splash Flip Meshing. Again, I will just simply load it from a file cache. Put down another null, call this here out flip fluid mesh. Put another box around here, call it flip meshing. Great. So here's the next part of this project, which is the infection solver. First of all, we're going to want to merge in our bottle, which is here, the bottle prep. Actually, no, sorry, it's the imported bottle. And we're going to want to split this into two different pieces. So we want the body itself, and we want the cap, which is this piece here. Next up, we're going to want to turn these here into point clouds. So let's do a point from volume. Put this here to 0.025, because we need plenty of points. We want to put the jitter scale to 1, and we want to create an output group actually. And the output group is just so we can separate these points from each other again later. So we can just do group underscore bottle body points. Then we copy this here over. And we call this here bottle cap points. And then we can merge these here back together. Put down a point wrangle. Say f at mask equals 0 here. Because what we're trying to do now is we will assign a attribute to the fluid and an attribute to our points here. And then inside of a subsolver, we will be transferring said attribute over from the fluid to our bottle. And afterwards, we will be using an infection solver to farther spread that attribute to areas that the fluid doesn't touch so that our bottle fills up nicely. The first thing we need to do is transfer the mass attribute over from our second input onto our bottle geometry. For that, we put down an attribute transfer, connect our previous frame here, and input 2 on the right. We want only the mask, and we want the distance to actually be fairly low. So 0.05 and 0.005 worked well for me here. Plug this into the output. Let's take a look if this works. Look at the mask and the display. If we look at this here and also template our points, we can see that wherever these points hit, the attribute gets transferred over, which is exactly what we want. Let's rewind to frame 1, dive back in here, and set up the rest of this. Here's a neat little trick that I use all the time, which Stefan Walch actually taught me. So if you take a rest position and you put down an attribute noise, let's set this here to 0 centered, amplitude 2, element size 4. We now have a noise stop geo. You can then use an attribute swap to change the rest with the position, or like to override the position with the rest. And now you can do all kinds of cool things on this noised up geo and then just swap it back, which is exactly what we will be doing with the infection solver to get a more broken up edge instead of like a very clean and uniform leading edge. The infection solver itself, I will not be going into too much detail. There is a great video on either YouTube or Vimeo, which I will be linking, which goes into detail and explains it. I will simply be copying over a chunk of code now. This code I will also either put in the description or you can just like type it from here. What we will want to do with this is that we want to put the search distance to 2 and the amount of points to 20. Now if we go into the output and we let this here play, what we're currently seeing is the mask value, which we don't care about right now. We want to see the infection value. So if you take a look at this here now and slowly scrub through, we can see that this is probably the hit from the liquid itself. But this little bit here is the infection happening. There we go. So we can see the liquids, but we can also see how we have this growth happening now with each of these points here. It's like looking for another point close by to them that is not infected and then passing them that infect attribute. So we can now put down another file cache, chuck this in here, subsolver cache, and then you can cache this. However, I will simply load it such as this. Put down another null, call this here infection solver cache, and we're good to go. The last step will be to actually take these infected points, turn them into a VDB, and then create this sort of VDB volume growth effect. Before we do that, let's clean up here, call this here infection solver, pull it to the side. And then let's pull our points from this infection solver cache into an object merge. So this step might be a little bit confusing, but bear with me. We'll get through this together. We have our infection solver cache, like the points here. We also need the imported bottle, which you can just copy over from here. Great. So we have this bottle here and the point. Let us now blast everything but the bottle itself away. Subdivide the bottle. Smoothen it out a little bit, and turn this bottle into a VDB. set the voxel size to 0.025. Need it to be a little bit more crisp. And now we have a VDB of this bottle. This here will become useful later. Now we hop over to our points here. We want to blur the leading edge a little bit. Put on an attribute blur, infect, and the influence type is proximity. And we want to set this here to 2 blurring iterations. Now we want to separate out the body from these points here, which is why we did the whole group in the points from volume. Put down a blast here, group, bottle body, delete non-selected. And now we want to grab all of these points that are actually infected. So we get rid of this purple stuff. Put down another blast, at infect is higher than 0.1. Put the group type to points. Now we will see, boom, we only have the infected points. So this is great. We will take this here, and now we'll turn these points here into an actual VDB. Let's do a VDB from particles. We need to decrease the point radius scale here a little bit to 0.05 because we have no p-scale on these points anymore. Plug this in here, and this minimum radius we will want to put to 0. Now this is still a little bit coarse. What we want to do is we want to actually link the voxel size from this bottle geometry to these particles here. Now we see, okay, looks a little bit bumpy. What do we do to combat that? We just do a VDB smooth. Set this to Gaussian. And now we have basically this whole like infection spreading, but as a VDB, as a volume. This does not have these nice crisp edges though that our bottle has. In order to get those back, we want to do kind of a Boolean operation in volumes. So we take a VDB combine, set this operation here to SDF intersect, and now we see that this looks very nice. Next thing we want to do is grab this leading edge here and kind of dilate the points here to make this leading edge a little bit thicker. In order to do that, we will blast some points again. This time we'll do at infect is above 0.45. Let's take a look at the points that we get here. Nice, so this is this leading edge. And then we will want to do another VDB from particles. Put this point radius scale to something smaller like 0.1. And turn this into a fog VDB. Also don't forget to link the voxel size again. Great, so now we have this fog VDB which we can use as a mask. We put on another reshape now. And we put this alpha mask here to density. And we put the offset to something like 5 or 6. We can see that only this leading edge is dilated now. Now we can do the same thing, but for blurring it or for smoothing it. So let's just copy and paste this. We're going to want to grab a little bit more. So let's do above 0.5. Let's also increase the point radius scale to 0.2, just to get a little bit more of a mask. Put on a smooth SDF. And now we can see that it has only smoothed these edges here. These corners are still crisp. Let's set this here to Gaussian. Now this looks pretty cool. The last thing that we can do now is put down a VDB reshape. And we're going to want to have this here match the actual size of our original bottle. So I will template this. And I want to erode this here just a tiny bit so that it matches the shape a bit better. 0.5 seems good. Last but not least, let's convert VDB back into polygons. And we have our bottle growth as a mesh. A little bonus trick would now be to get the UVs that we have over here. Well, these look very messy. To get these UVs onto our mesh as well, in case you want to use them. What we can do now is just put down an attribute transfer. Sorry, not UV transfer. Attribute transfer from the subdivide to this convert VDB. We don't want primitive, not points. We want vertices. There we go. Now we have the UVs on our VDB as well, or on our VDB mesh. And another extra trick would be to solve the question of how can we actually get velocity on this leading edge here. because like it's growing into a direction, right? So it won't make sense to have some kind of motion blur on it. The way that we can do this is also fairly simple. We just put down a point triangle, grab this leading edge here, put it in the first input and into the second input. However, we'll want to just hook up a time shift into the second input here and subtract the 1 from the time. So it's $f minus 1. Then we want to grab the position, like the old position, which is this one, and subtract it from the new position. So we'll create vector old pos, which is the point function, 1. We want the position from each point number, more like each point, and the new position, new pos, is just our current position. So now our velocity, we will just want to normalize this, is our new position minus our old position times a multiplier. I forgot the backticks here. There we go. So that's the code. We'll just activate this, set this multiplier to 1. And if we look at this here now, we will see that we have velocities. Put down one more attribute transfer. Transfer from this point triangle to this previous attribute transfer. Put velocity in here and decrease the distance threshold. Let's actually take a look. So we only want this here on a leading edge. So maybe something like 0.3, I suppose. Let's also increase the sample count to blur this here out a little bit more. Okay, great. Now we can just put down a file cache and cache this here out. VDB mesh bottle cache. I'll just simply load this cache from my disk again, putting down a file. Put down one last null, call this here out bottle body mesh. Put a nice box around it. VDB, or actually meshing bottle. Now I can just copy and paste this whole thing to do the same thing for the cap. We just copy and paste this. However, we do not want the bottle, we want the cap, which means this here. And then here, we don't want the bottle body points, we want the bottle cap points. So let's take a look. Yeah, this looks good enough. I'll buy this. We just gotta double check if the velocity is only on the leading edges, which yeah, it looks like it. Cool, so now we'll just call this here mesh cap cache, and you can just cache it out. I will simply load it in. Don't forget to change the null here, bottle cap mesh, and this is pretty much it. So the setup is done now. We can simply hop out here, put down one null as our hero controller. Forgot a null there. And then we can put down 3 geo containers. So one will be render bottle body, one will be render bottle cap, and one will be render fluid. Let's make these red and connect them to the hero controller. Let's object merge these things in now. So we want to object merge our bottle body. Then we want to merge our bottle cap and our flip fluid mesh. Great. So if we look at this here now in the whole like context of the scene, I believe that this bottle is a little bit too large. So we can just use the hero controller here, scale this here down by a factor of 0.25, and we can just readjust our camera a little bit. So let's just go like this. Maybe, yeah, like 11 works. Let me add a null to give it a little bit of a rotation on the X. And we can look at it from a little bit from below and a little bit from the side. What we can do as the last thing now is just rotate this, see which direction looks the best. Let's just go for, let's go for this side. I'll just say. Cool, and that's pretty much it. Thanks for watching all the way through. I hope you enjoyed the tutorial. Please tag me on your renders as @danielgoetz.exr on Instagram and @danielgoetz_ on Twitter. I can't wait to see what you'll come up with. Make sure to subscribe to my YouTube channel @danielgoetz to not miss part 2 of this tutorial, which will be all about rendering. See you there.